This whole project started because I wanted to be certain about the wire choice we were making in an 1867 Chickering 33B. And it seemed that 1867 was long enough ago that there may be real differences between the wire employed in that piano and wire as it's used today, or wire as it was used even 30 years after that. And it's still 1897, so the question arose, how would we choose the right wire? Wire's been part of piano making from the very beginning. I don't think they're quite certain what Cristofori's first piano was strung with, but they're sure it was either brass and bronze wire or soft iron wire. These metals had been employed in the harpsichord, so their employment in the piano was only natural. But pianos and wire have been inextricably bound together ever since, because if your wire is only so strong, no matter how you care to construct things, you can only build a note so long out of that wire, no matter what note you're referring to or any point in the scale. So as wires got stronger, pianos got bigger. Now there's a number of things you can do with a stronger wire, not just make your piano bigger, but for a long time that intrinsic limit was what kept grands being built in a certain length range. And you can only tell so much about a note by measuring its length and its diameter and its frequency. You can learn how much tension the wire is under, but you're still left without any idea what percentage of that wire's capacity is being used. How hard is that wire being worked? And that seems to be a really important parameter in the scaling. And so, since we really can't get a proper tensile stress machine, there's another route. And that route is, in theory, the hardness of the wire. It's fairly well documented that music wire over the decades, especially during the mid and late 19th century, was becoming progressively stronger and stronger wire. And as a result, bigger and bigger pianos could be built. The question is, as music wire got stronger and stronger, did it at the same time get harder and harder? The connection between tensile strength and hardness is a pretty well established and accepted inspection process for modern music wire. The question is, does this hold true through the history of the development, or is it a slightly more complicated situation? Which leads me to this beautiful object you've no doubt been admiring while I have been soliloquizing. This is an early Rockwell hardness tester made by the Wilson Company. I think it was made in the early 30s. That's the last patent date on it. And it has a 3-digit serial number. So this is a real pioneer in the industry. In oversimplified terms, what the Rockwell hardness tester does is measure the hardness of metal by measuring how far a given weight will push a little diamond pointed indenter into it. Up top you can see the weight, you can see the little pencil point indenter and the graduated gauge. And it has become one of the basic measuring tools of all machinists. So I want to take a closer look at it, how it works, and show you it in operation. The way this version of the tester works is pretty straightforward and quite elegant compared to other models. There is a weight here at the end of this lever, and that weight is compounded from this hinge over to this linkage, multiplying it however many times, and this linkage bears that force down on the end of this extremely long lever that, when it comes over here, pivots on that knife edge and concentrates all that concentrated force onto another knife edge that goes down into the diamond indenter. Now, any piano technician would look at this and say, oh, but yes, of course. We work with such leverage ratios all the time. Just we're trying to throw this weight around, not concentrate its energy down, but that's how this one works. And the real technology is in that diamond indenter. Take a quick look at that gem. Kind of at the extreme focus range of this camera, but I wanted to see if I couldn't get a close look at the diamond penetrator. What it is it's a diamond, and it has been lapped into a conical shape. It has a perfectly spherical point of some particular dimension, and the rest of it is a cone lapped out at a specified angle, and it is used as the universal indenter for very hard materials. There is a second indenter that uses a carbide tip ball. I'll show you that now. This is the other indenter, and it is just another mounting that has a screw cap on the top, and it traps that little carbide ball. And the carbide balls are replaceable because they can be deformed, and they're used to test softer metals like brasses and bronzes. So and this allows you to, this is just allows for greater range of applications, because the diamond can be far too hard for some of the softer metals, and it'll just go beyond the machine's range of measurement. So another really important component in this machine is the oil damper, and it's basically a plunger that goes down into that brass cylinder, and it's got a plate on it with little relief holes, and what it does is stop the weight from dropping at gravity speed. As I said, the diamond is hard but not particularly tough. So in order to keep the diamond safe and to keep the test consistent, the weight has to be lowered at a very consistent speed, and that's what this does. So when you see the hammer falling so smoothly, this is the part that does it. Since the purpose of the machine is to test the hardness of a piece of metal, the machine itself has to be tested for accuracy, and that is done with one of these, or a series of these actually, small, light, or soft, medium, and hard. This is the medium block, and they're tested, and the hardness is determined to usually a 1/10 of a degree plus or minus a whole degree. So these are relative hardness testing machines, but they can be quite accurate. And to demonstrate this one, I will show how the system works. The sample is placed on top of the column. And the column is raised the sample comes in contact with the diamond. And since the diamond is very hard but not very tough, this is kind of a gentle operation. And when you see the needle twitch, you're there. The next step is to add the minor load. And the minor load is about 10 kilograms inside the machine. And you can see the little dial spinning. And when it gets up into the colored zone, the minor load is applied. Zero out the gauge. And release the major load to descend. Give it about that much time. And you take the major load off. And the dial indicates the relative hardness. This reads 45 almost exactly. And that is within 1 point of 45.8. So this machine is working quite well. Now the hard test block is rated at 73, which I gather is about the hardness of tool steel. So find a nice clean spot. Again, raise it up to contact the diamond. Raise the minor load. Zero out the gauge. when the load is lifted. Dial goes to 73.5, which is precisely what this block is rated at. Oh, my mistake, it's 73.0 plus or minus 5. So again, we're within the range. Well, I hope this served as a reasonable introduction to the question why I want to study the hardness of piano wire, especially historical piano wire. And I hope this served as a good introduction as to what the machine actually does. Now, how do I get that to do the same thing to that? And that was a bit of a struggle all its own, and I'll cover that in the next video. But thanks for watching.